G'day, let's continue this series on electrochemistry. Looking today at calculating standard cell potentials, where we're going to calculate these, given these symbols, and use these values to determine the feasibility of a reaction. So leading very logically on from last time, where we were discussing the fact that we can get reduction potentials by measuring all our half cells relative to a standard at standard conditions, the standard being that standard hydrogen electrode. Let's now start to look at what happens when we connect half cells where we don't have this standard hydrogen electrode. So just to remind you, the standard electrode potential is a half cell's electrode potential measured relative to the sheet, the standard hydrogen electrode, where this value indicates how easy it is to reduce. So let's remind ourselves what these values are telling us. The more positive it is, the easier it is to reduce. So recall that I'm always writing the forward reaction as the reduction reactions, just the convention that I'm using. So the more positive this value here, that's implying the more that forward reaction is favorable. And if we look at these species that I've got here, it makes sense. You know, if you think about our very unreactive elements, they very much want to be in that, they don't want to lose the electrons, they very much want to be in that atomic metallic form. So it makes sense that things like copper and things like silver are very much going to be favoring the forward reaction and much more easier to reduce. And we'll look at the converse of this in a moment. But we can put this in some other words. We can say that therefore it's harder to oxidize. So the backward reaction is much more unfavorable. We can also talk in terms of its reactivity, which we just did. So if we look at our positive species here, silver, copper, we very much know that they're unreactive elements. And finally, we can also talk in terms of oxidizing and reducing agents. So let's recall what these terms are referring to. If something's been oxidized, it's losing electrons, but it needs to provide those electrons to something. The redox has to have both processes. So if the species is being oxidized, it's causing the other thing to be reduced. So the species being oxidized is a reducing agent. Conversely, if a species is being reduced, it's gaining electrons. It's got to gain those from somewhere, so it's causing something to lose them. So the species that is being reduced is acting as an oxidizing agent. We can also use the terms reductant and oxidant as synonyms for these. So if something's easy to reduce, it means it's going to be a poor reducing agent, or we can say it's going to be a good oxidizing agent. So using all of this vocabulary to describe what these reduction potentials are telling us. So let's sort of reiterate all that by looking at what a more negative value is telling us. It's telling us that it's harder to reduce. So let's look at our negative values here. We've got something that's very negative. So that's saying that this forward reaction is very, very unfavorable. And that makes sense for something like lithium. We're going to talk in terms of reactivity again. Super reactive. Group 1 element does not want to exist as that metallic form. It wants to be oxidized into the ion, and that's what this negative value is telling us. Now, when we talk about the reduction potential in the opposite direction, we could talk about an oxidizing potential, right? So if it's minus 0.3 in this forward direction, then it's going to be plus 0.3 in that backwards direction. So again, that's also implying that it very much wants to be oxidized. It favors the backward reaction there. What else have we got? So manganese, negative value. So that's telling us that it's harder to reduce or easier to oxidize. Zinc, another example there. So we can use all that vocabulary again. So if it's harder to reduce, then it's going to be easier to oxidize. If it's harder to reduce, it implies that it's relatively reactive because it doesn't want to stay in that form. It wants to go to the oxidized form, at least with respect to our metals here. Thus, we can say it's a relatively good reducing agent, or we could say it's a relatively poor oxidizing agent for all of those reasons that we just described before. So lots of vocabulary. It's important that we're clear on these terms, and we'll practice this in just a moment. So essentially, if we combine two half cells, you combine that one and that one, or that one and that one, we can get a standard cell potential, so still under our standard conditions with our plimsoll sign there, which is going to be the potential difference, so the voltage generated, essentially the electrical energy produced between the anode and cathode of the galvanic cell, where one of them is going to undergo oxidation, one of them is going to undergo reduction, and we have that flow of electrons, which is the electrical energy. We'll get to that in a moment. I've got a whole bunch of reduction potentials here. Based on what we've just been talking about with ease of oxidation or ease of reduction, in terms of reducing and oxidizing agents, see if you can answer these 4 questions that are on the right-hand side, 3 of which you're identifying, what is the easiest to reduce, so on and so forth. And the 4th one is having a go at drawing the electrochemical cell. So give that a red hot try if you're so inclined. If not, let's have a talk about some answers over here now. So our first question there, which metal is the easiest to reduce? We're thinking in terms of a positive reduction potential. The more positive it is, the more that reduction reaction is favored. So we want to find the most positive value, which in my little list of 5 here is going to be silver. And that makes sense because silver is very unreactive. Why would silver want to remain as the silver ion? It very much wants to be reduced to the silver atom. So which above is the most reactive? So you got to think in terms of how our metals are reacting. Our metals react by being oxidized. A negative reduction potential tells us it's a really good, it's very favorable for it to be oxidized. So we want to find our most negative there, which is clearly the lithium up the top there. Which metal is the best reducing agent? If it's a reducing agent, it means it itself is oxidized. So again, we're just trying to find the one that is the most likely to be oxidized there, and that's going to be lithium again. So now we were drawing a whole bunch of galvanic cells with our standard hydrogen electrode last time. Let's have a look at what happens when we combined 2 half cells where we don't have the sheet, which is what I've asked in this final question. Should be a little plus there, Cu2 plus Cu, and the zinc 2 plus half cell. So let's have a look at that now with a nice little diagram I've made with all my shapes on slides. It'll look something like this. So copper, zinc half cell. Doesn't really matter which one you put on either side, unless you've been specified to put one on a particular side, like in terms of the anode and cathode I'm talking. But as long as everything's annotated correctly relative to each other, it shouldn't present too much of an issue. So what have we got here? We've got our standard conditions. So these are both metal ion half cells. So that's what I'm showing there with my electrodes and my ions in solution. And we're at standard conditions, so 1 mole per decimeter cubed solutions. Rightio, let's have a talk about these reduction potentials. As we do with these galvanic cells, we've got to describe the anode, we've got to show the oxidation reaction, the reduction reaction, show the cathode, and then we're going to go a step further and calculate the voltage that is generated, the potential difference generated. So how do we know which is oxidized and which is reduced? Well, we use what we just looked at. We've got a whole bunch of reduction potentials, and we know the more positive, the more it's going to want to be reduced. So let's have a look here. We got copper and zinc. So we got copper up there and we got zinc down here. So the more positive one is the one that's going to drive to be reduced, and the more negative one is the one that's going to be drive to be oxidized. So up here, our copper is very much going to proceed in the forward direction, and our zinc is very much going to proceed in the backward direction based on these values that we have. So we can annotate accordingly on our diagram over here. So on the left-hand side, we're going to have the reduction reaction, which is the more positive. Just a reminder, these are saying that this is generating 0.34 volts more than hydrogen in the standard hydrogen electrode. So they're all relative values. But if this is our reduction, that means that we very much have our cathode on the left-hand side here, and oil rig cap. That means that our oxidation reaction has to occur over here at what will be our anode. So that's our more negative one. And again, this is saying that this is generating 0.76 volts less than hydrogen in the standard hydrogen electrode. So now, when we had the standard hydrogen electrode, we had one of the values just as 0, right? So we could just get the value pretty easily accordingly. In this instance, we got 2 values. So if we want to get the total cell potential, the total potential difference being generated when we combine these, we've got to do some mathematics. So let's have a look down here and we'll get to that second point there in just a moment. So we can do an overall equation. Actually, before we do that, we can do an overall equation, because if we know that the zinc is going to be oxidized, we know that this reaction is going to proceed in the backward reaction there. We know the copper is going to be reduced. We know this is going to proceed in the forward reaction there. This is stuff we've all done before. We can balance our 2 half equations, the reduction and oxidation half equation, make sure the electrons balance, in which case they do, and you can combine them and we can end up with an overall equation for this redox that is occurring. And we can do that annotation of our half cell that we looked at last time as well. So now, how do we calculate the standard cell potential? I'm going to talk through two methods which essentially are the exact same thing. It's just that sometimes, people talk in different terms. So hopefully without getting too confusing, I'm going to show you the exact same thing twice, essentially. It's just certain people might teach it one way, certain other people might teach it another way. They're teaching the same thing. So let's have a look over here. Two methods for calculating the standard cell potential. If you change the sign to get the oxidation potential for the oxidation reaction, then you can add them together. So this is saying that you can get the reduction potential because this reaction's going to be reduced, so we get that value there. And we think about in terms of the oxidation reaction, which is the backward reaction. So we change the sign there and we add them together over there. That's one way to think about it. The other way to think about it is you don't change the sign and you think about the reduction potential at the cathode and the reduction potential at the anode. So this is saying that you get your cathode reduction potential, which is plus 0.34 volts, and then you subtract your anode reduction potential, which is minus 0.76 volts. But what you've probably already realized, and like I said just before, you're doing the exact same thing no matter which way you think about it. Because if we have a oxidation potential where we flip the sign up here for the backward reaction and we add them together, that's going to be the exact same thing as not flipping the sign and subtracting them, because if you got a minus and you multiply that minus by whatever your sign is, you're going to flip the sign anyway. So it's a bit confusing that if you do encounter both. I recommend this one, and that's the one I'm going to do from this point forward. I think that's much more intuitive to think in terms of a reduction reaction, to think in terms of the oxidation reaction. And we've been looking at flipping signs for the reverse reaction and all sorts of things. And enthalpy, this is just another one for our electrochemistry. So look, have a go at that now and see if you can calculate the standard cell potential for our electrochemical cell using whichever way you think is better to think about it. But like I said, that's my recommendation there. So our reduction potential, our reduction reaction is going to be this one. So we're going to have plus 0.34 volts. And we're going to add that to the oxidation potential, which is the backward reaction. So we're going to flip that sign, and that's going to mean that we end up with 1.1 volts. Look, for the sake of rigorousness, let's just think about it the other way as well. If you got your reduction potential at the cathode, you're going to have plus 0.34 volts because that's our reduction reaction. And then you're going to minus the reduction potential at the cathode. So if we don't change the sign, minus 0.76 volts. But what do you know? You end up, of course, with the same answer because that's what this minus is doing. It's flipping the sign anyway. So hopefully that didn't confuse you too much. If it did, disregard everything and just do that. All right, next bit. Let's talk in terms of reaction feasibility. Just like you might use the word feasible in your everyday vocabulary, it's describing a similar sort of thing here. Reaction feasibility, quite simply, is the likelihood of a reaction occurring between certain reactions. If it's feasible, you'd expect it to occur. If it's unfeasible, you would not expect it to occur. Like I say, very similar to our everyday vocabulary of that word. The potential difference can be used to assess the feasibility of a reaction. Where the more positive our value is, the greater the likelihood of the forward reaction occurring, whereas the more negative, the greater likelihood of the reverse reaction occurring. So just a little question in here. Thinking in terms of using that vocabulary of feasibility, which reaction is more feasible and which reaction is less feasible in these two redox equilibrium? So pause now, give that a go if you like, but it's reiterating what we've been talking about. So the fact that this is a positive value for our reduction potential there, that's going to favor the reduction direction, which is the forward reaction. So we can say the forward reaction is the more feasible, whereas below it we have a negative, which implies the oxidation direction, which means the backward reaction is going to be more feasible. What have we got here? If the forward reaction is feasible, then the backward reaction will not be. A reaction always occurs in a direction so that the stronger oxidizing agent reacts with the stronger reducing agent, which makes sense if you think about it. The one that has more desire to lose electrons is going to drive that reaction to make sure that that happens. Let's look at two examples here. And considering which is the stronger oxidizing agent and which is the stronger reducing agent based on our information up here, determine which of the reactions below is the feasible reaction. Pause, give that a go, and let's have a talk about it. So what's going on over here? We have zinc going to zinc ions, right? So that's saying that this reaction would be the oxidation. This is the one that wants to be oxidized more. It's the more negative value. So this would be the stronger reducing agent, and our copper ions going to copper, that would be occurring in that direction. So that would be the one that would want to be reduced. So that would be the stronger oxidizing agent. So in this instance, yes, we have the stronger oxidizing agent reacting with the stronger reducing agent. So we would expect to see a reaction occurring there. Cu2 plus is the better oxidizing agent, the better oxidant, as seen by the more positive value. Whereas let's consider this one over here. We have copper going to Cu2 plus. So we would have this going in that reverse direction, and we would have zinc 2 plus going to zinc. So we would have this going in the forward reaction. But we have the more negative value would not be reduced. The more positive value would be reduced. So this reaction would not be feasible. We would not expect anything to occur because we don't have, neither of the half reactions are feasible. The stronger oxidizing agent is not reacting with the stronger reducing agent. So therefore there will be no reaction there, but there will be a reaction over there. Let's continue talking about feasibility, and let's link this to our cell potentials, because we can calculate cell potentials to determine the feasibility of a reaction occurring. So what do we have here? Our reduction potentials are often given in descending order. So we can compare two half cells and we can predict the feasibility. So that's what I have over here. I've got a big table of some reduction potentials I've picked out, and I put them from the most positive down to the most negative. We have our standard hydrogen electrode in there with its 0 volt as the reference point. Let's consider what this is telling us. So more positive, the easier to reduce, the more feasible the forward reaction there. The more negative, the easier to oxidize, the more feasible, the backward reaction there. We can think in terms of oxidizing and reducing agents. So easier to reduce means it's a stronger oxidizing agent for all those reasons we've discussed. Easier to reduce means it is a weaker reducing agent. The opposite of that, more easier to oxidize means it's a stronger reducing agent, and therefore it's a weaker oxidizing agent. All right. The stronger oxidant can oxidize the stronger reductant, and this will make a clockwise direction, which I'll explain in just a moment. So I've got some questions here. Let's go through the first one, or if you just want to skip ahead, you're in control of your computer there. Do as you want to do. But I'm just going to dive straight into this first one. It's asking, will I2 oxidize Fe2 plus to Fe3 plus? So let's have a look at what's occurring here. I2 over here. Will I2 oxidize Fe2 plus to Fe3 plus? So our Fe2 plus and Fe3 plus is over here. So if this is being oxidized, this would be occurring in the backward direction. Whereas if this was that would mean that this would have to be reduced. This would be acting as the oxidizing agent. But in fact, we have a weaker oxidizing agent and a weaker reducing agent. So in this instance, the stronger oxidizing agent is not oxidizing the stronger reducing agent. So we would not expect this reaction to be feasible. And this is what I've written here. It'll always make a clockwise direction if the reaction is. So if this is going this way, that's anti-clockwise. So that means that no, that reaction is not feasible. So look, based on that, if you want to give the other few a go, you're more than welcome to. We'll just carry on going through and explaining them. So will the copper react with zinc? So where's our Cu2 plus? Will Cu2 plus. So if that's going to react, it's implying that's going in the forward direction. Will that react with zinc? So if the zinc's reacting, it's implying that's going to go in the backward reaction. So to go back to our clockwise direction, straight away we can see that this arrow, maybe I'll use green, is going in a clockwise direction. So that's going to tell you straight away that yes, this is a feasible reaction. Let's think conceptually as well. Copper is above the zinc. So copper is the stronger oxidizing agent. The zinc is below the copper, or the copper ions there, so we have the stronger reducing agent. So that all checks out. So yes, we would expect this reaction to occur, and we can write an equation accordingly to show that chemical change. Next one, will silver react with copper ions? So let's have a look at our silver here. Silver is there. So if this is reacting, then that means it's being oxidized. The silver reacts through oxidation, and the Cu2 plus would react there. So we've got the anti-clockwise direction. So no, we have a weaker reducing agent reacting with the weaker oxidizing agent. So that absolutely would not occur. And then the final one, will Cl2 oxidize Fe2 plus to Fe3 plus? Let's have a look up here. So Cl2 is acting as the oxidizing agent. So straight away we have a stronger oxidizing agent, Fe2 plus to Fe3 plus. Down here we have the stronger reducing agent. Below it we have the clockwise direction. Yes, that will occur, and yes, we can write an equation to show that. We can also calculate the cell potential to determine the feasibility, where the same principles are applying. If we end up with a positive cell potential, it implies the forward reaction is feasible. If we end up with a negative cell potential, it implies the forward reaction is not feasible. And that's going to reiterate our results that we see over here. So let's very quickly calculate some of these. So I2 was this one here, and Fe2 plus to Fe3 plus. So let's get our reduction potential, which would be plus 0.54 volts. And then let's add that to our oxidizing potential. So we have the negative 0.77. That's very much going to give us a negative value there, which means that, oh, there we go, that's just what we said. There's the equation there. So that means that we're going to end up with a negative cell potential based on that calculation I just did. I just drew up. So that would say that no, that is not a feasible reaction. If you want to use that to calculate the rest of them, more than welcome. Let's continue 3. So this one, yes. So we would expect a positive cell potential to be the result of this. So we have Cu2 plus going in the forward direction, going from Cu2 plus to Cu, and we would expect the zinc to go in the backward direction because we're going from Zn to Zn2 plus. So what do we have? We have a positive reduction potential, plus 0.34, and let's add that. Let's flip that sign. So that's going to be 0.76. And in fact, this is the one that we just did on the previous slide, wasn't it? So that's going to end up with 1.1 volts. Continue through, silver with copper. So the silver's reacting and the Cu2 plus is reacting. So we have the oxidation potential here, because this is going to be the reverse. So in fact, let's be consistent. Let's start with the reduction potential, which is going to be the 0.34 volts. If we were saying this is going to occur, then this one's being reduced. And then we plus that from the oxidation potential, which is in the backward reaction. So we have to reverse that sign. So if we got a small number and we subtract a bigger number, we're very much going to end up with a negative value there. So no, that is not feasible. And the last one, which we decided was feasible, we would expect another positive value. So we have Cl2 going in the forward direction, so that's our reduction potential. We have Fe2 plus going to Fe3 plus, so we can swap the sign there to get our oxidation potential. And let's add those together. So we're going to end up with 1.36, and we're going to plus minus 0.77. Even though we're subtracting a number, we're still going to end up with a positive value there. A good thing to do is to put positive signs in front of these. I haven't done that, but I've just corrected that then, so that's a good thing to do. And look, that concludes our lesson calculating standard cell potentials. What have we done? We calculated a standard cell potential by combining two standard electrode potentials, and then we use standard cell potentials to predict the feasibility of a reaction, deduce the polarity of each electrode, and hence explain, deduce the direction of electron flow in the external circuit of a simple cell. Look, that's something that we looked at a bit more in the previous video, but just to quickly cover that now, that's just saying that we can identify our oxidation and our reduction reactions in our galvanic cell, and that allows us to show the electron flow by assigning, if we've got a reduction, we've got a cathode over this side, an oil rig cat. If we have the oxidation, we have the anode over this side. So that's our oxidation reaction, that's our reduction reaction. So the electrons are being lost at the anode and then moving through to the cathode, showing that electron transfer, that electron flow like we did previously. And then assigning the polarity, the anode in a galvanic cell is negative, a cathode in a galvanic cell is positive. And then we could even assign our salt bridge ions to show that we have the neutrality of our solutions remaining. So let's consider this. We have Cu2 plus going to Cu, so this is going to get less positive. So we need some positive cations to go down and deal with that, for lack of a better word. And then over here we have the oxidation reaction. So we have our zinc metal going to zinc ion. So this is going to get more positive. So we need our negative anions from the salt bridge to go down and ensure that remains neutral. So there you go. That's just a recap of something we've looked at previously. Let's get to the tasks. So you can pause should you so choose. Work through those one column at a time from the bottom to the top. Brilliant. Well done. Good job. I'll see you next time.